welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
I would like to thank you all very much for joining this event. I would like to introduce to you the topic of fast and accurate multiport IL and PDL testing. And I would like to cover in today's talk first a brief introduction about the industry drivers, what makes the industry move in these days, and at the same time the requirements for test equipment. They are moving and changing as well. This leads us to the topic of then Polarization Dependent Loss, PDL, and we will discuss the importance of that as well as measurement methods and Agilent's test solution for that topic. We will look at the measurement results for specific components, and at the end I will provide a summary. Looking at today's industry, telecommunication industry, we see that over the past decades there has been a dramatic change in this industry. We see that the pace of the change is really increasing. There are lots of things happening, and what in particular is impressive, for example, is the growth of the traffic in the internet. Today, YouTube generates as much traffic as the whole industry demanded in the year 2000. And one additional interesting data point is that a very important driver for bandwidth in these days is also the financial community. So, for example, the New York Stock Exchange is one of the first customers really driving and asking for 100 gigabit per second connections. This, along with the demand at everybody's home for high-definition TV, for mobile services, and so on, drives really the traffic demand, and therefore also causes a significant evolution of the network. And the fundamental directions of this evolution, that is really can be summarized in three main categories. One category is the capacity, speed, needs to increase all the time. Right now we look at 40 and 100 gigabit per second solutions, and that is going to be implemented in combination with advanced and complex modulation techniques. This has as a consequence, of course, that you are running tighter against the margins. So the margins get smaller. You are closer to the physical limitations of the network, of the fiber. And the next fundamental direction, and that is that you would like to have more flexibility. You would like to provide capacity on demand, and this drives the topic of switching in the optical domain. So components like ROADMs or tunable transponders get of increased importance, and they are moving into the networks today already. This photonic switching has as a very important consequence that the optical length of the transmission link is going to be increased. So you have longer length and more components are adding up in their characteristics. And the third fundamental direction we see in the networks is cost reduction. Reduce costs wherever possible. That means the level of integration, of course, is going up. You try to integrate the photonic components. That's one direction, but another important point is really one of the key drivers for cost in networks is power consumption, and therefore having power efficient electronics and systems is also of very high importance. These are now the fundamental directions, but the question is, what does that mean for the test and measurement industry? And of course, first of all, the cost of test has to be reduced. This is very important, and this is supported by test automation. So the test needs to be automated so that the throughput can be increased, and automation then again requires certain instrument properties. For example, we need certain interfaces on the instruments. Local area network connection is important in these days. If you have local area networks, then in many cases you don't need a GUI anymore. Of course, small footprint is also highly desired, and I already talked about the speed requirement, which is more or less identical to throughput. Agilent addresses these requirements with a new series of optical test instruments, and we will talk about some of these instruments during this session. We started discussing PDL, and what is PDL and why is it important? First of all, PDL is called Polarization Dependent Loss. And you can imagine that is when you couple a signal into a fiber, then the signal travels down the fiber or travels down the component. And in case you couple in one polarization, for example, the polarization which is indicated with red color here, you may have one type of attenuation constant. And if you couple in another polarization, which is indicated here with a blue-green color, then you may have another type of attenuation. That means, depending on how the signal travels down the fiber, you may have more or less loss on the link at the end. Or briefly in summary, different loss of the traveling signal for different launching polarizations. That is PDL. So networks, as we discussed before, consist in these days of many fibers, many components, and with photonic switching and so on. These are combined, and so you have many sources of PDL combined along a fiber optic link. If the polarization changes along the link, so in between these PDL sources, then you get the effect that these PDL contributors, they add up in a statistical way. That means some of them may really add up, and some of them may cancel out. And this means that at the receiver side, you have to expect significant power variations upon polarization changes. Variations of several dB are currently observed in networks, and that means that at the receiver, the power level moves up or down by several dB, and therefore the power margins have to be budgeted accordingly, and also the decision threshold of the receiver has to be able to track these changes, for example. And these are severe issues when you're getting closer to the physical limitations of the transmission, as we discussed before. So PDL is important, and now we have the question, how do we test PDL? And there are a number of methods in the industry established, and I would like to introduce some of these methods. And there's in particular one method which has been used for a very long time and which is still being used in some cases, and that is the so-called all states method, or the polarization scanning method. In that case, you have an optical source, a laser for example, and that source is guided through a polarization scrambler. So the scrambler just changes the polarization in an artificial way, in a random way, which means that the device under test is exposed to many different polarization states, and I would say it is exposed to basically every state which you have on the Poincare sphere. As a result, you see power variations on the output side, and by taking the minimum and the maximum power level and taking the ratio, you get the PDL value of that component of the device under test. This method, as I mentioned, is broadly used in industry. It has been used for a very long time because it has significant advantages. For example, it is a very simple setup. It can easily be implemented at various wavelengths because there are not so many requirements on all these components, and it also has been proven that it can be very accurate. On the other hand, there are severe shortcomings, and one of the most important shortcoming is that this method is rather slow. It is slow because you have to wait at every wavelength that the Poincare sphere is more or less covered by all the polarizations. That means you typically use a fixed laser, or you use a lambda stepped laser, a laser which is stepped through the wavelength range. You cannot really use a continuously tuning laser because then you do not have enough polarization information at every wavelength. For that reason, highly resolved spectral measurements are basically not practical. It just takes too long time stepping through the wavelength range. And what you also should be aware of is that the scrambler, which you use for generating the various polarization states, generates insertion loss variations. And these insertion loss variations, they are included in the measurement results. So if the scrambler has high variations, that compromises your accuracy. And in order to move to a practical way to measure broadband components as you have them in WDM systems, the Müller matrix method was invented several years ago. And this method basically uses a different approach. So this method considers that you generate a number of states of polarization, and the number is typically 4. And by generating these 4 polarizations, you quickly sweep through the wavelength range with the source on the launching side, and that source therefore can be, for example, a tunable laser. So you take for the 4 different states the power traces on the output side, and afterwards you do the calculation using the Müller matrix method to obtain the PDL. This method is also broadly used. It is proven that it is fast, so you can operate the laser in a continuous way, and also therefore it is practical to really make highly spectrally resolved measurements. There are also here severe shortcomings, and one shortcoming is, for example, that the Hubble measurement is highly susceptible to vibrations and drift of the fibers in the DUT. So if there are any changes of conditions, any drift in between these 4 sweeps, then that influences heavily the measurement result. The same is true if the laser is not repeatable regarding power and wavelength. So the laser really has to have the very same power, the very same wavelength with every sweep. If there are differences, then this also has an immediate degradation of the result as a consequence. And of course, these shortcomings, they lead to the point that there is a need for a better solution. And Agilent would like to introduce the single sweep PDL method. And this method works in a slightly different way. So this method collects all the measurement data in a single wavelength sweep of the laser. So we do one sweep and we collect all the data we need to do the PDL calculation. That is done by the following, as I explained here in the following bullet point. While sweeping the laser, the polarization is switched periodically within a set of states of polarization. So we sweep the laser across the C or the C and the L band, for example, and very quickly we switch with this polarization synthesizer to a set of polarizations. This polarization synthesizer contains a lithium niobate polarization controller and therefore can switch with very high speed to the various states. On the receiver side, we are using the new Agilent multi-port power meter. This is a new power meter which contains a proprietary design so that we can cover a dynamic range of 60 dB without doing any gain switching inside that unit. This one, in combination with the high sampling rate of the power meter, allows us to capture all information which is generated within this single sweep of the laser. The measurement results are then analyzed in the computer and provided to the user. This method has a number of advantages, and so this method is really fast. So we talk here about measurement times in the area of seconds and not of minutes. In particular also, this measurement here is robust against fiber or DOT movements, because the measurements which are at the end correlated to be one PDL value, these measurements, they are taken within a few milliseconds or even less than a millisecond, so there is not much time for movement and drift. And also the issue of power and wavelength drift of the laser has been eliminated, because we only have one sweep, and therefore we do not need to be careful to have repeatable behavior between multiple sweeps of the laser. As we will see later on, this provides us with the capability to have a dynamic range of about 60 dB in a single sweep of the laser. Looking at this method, we see that there are a number of benefits. It's obvious that this high measurement speed is of a significant advantage, because this just provides us throughput. And typically, there are measurement times around 10 to 20 seconds for 40 channels for the C and the L band of a component. The precise numbers, of course, they depend on various details, and that includes, for example, the processing speed of the laptop computer, of the computer which is involved. The high dynamic range of the power meter, that has a number of advantages, and one of the advantages is that the minimum noise which is here contributed eliminates the necessity for averaging multiple measurements. So you just do one measurement and that's it. And the robustness just means that you do not need to consider drift, vibration, and so on in your measurement results. So you can have high confidence in the measurements, high reliability. You have maximum yield when testing your components. This is a multi-channel measurement setup, and you can scale the channel number by multiples of 4, and this can be done up to several hundreds of channels, and so you can scale it really to the number whichever you like. And as we will see very soon, we have a very high density of channels. So we have 16 channels in a 1 unit rack height. Here we see one typical implementation of a system. So on the top of this instrument pile, we see the multi-port power meter with 8 fibers connected. The instrument in the middle, that is the polarization synthesizer, which switches quickly between the polarization states. And on the bottom, we see Agilent's compact tunable laser. It's a compact laser which can sweep continuously across the C, across the C and the L band. All this is controlled by the computer, and the computer is running Agilent's new software package. That is the N7700A photonic application suite. And this package, as we will see later on, supports you in doing all these measurements. The compact laser can also be exchanged by Agilent's 81600B series of lasers, which provides higher performance and at the end might provide better signal quality in measurement quality in some measurement applications. Here we see an implementation of a 40-channel system. So we have here on the table a multiplexer, demultiplexer with 40 channels, and we have 5 multi-port power meters here on one pile, and these 5 power meters, they allow exactly connecting these 40 channels. We again have here the polarization synthesizer, and we also have in this case a full-size tunable laser as you see it. When talking about such a large number of connectors, like 40 connectors, you probably appreciate that the measurement time is only one of the issues which needs to be solved. So one other key issue is the connectivity. If you want to have a good usage of your test system, you really need to make sure that the system is measuring and not being tied up by connecting the next device under test. And looking at all these connectors, as you see it here at a previous generation measurement system, you can imagine that it takes quite a long time to connect all these fibers, and during that time the system is not available for measurements. So Agilent has introduced improvements in this area, and what is really providing a great advantage here is the new snap-on 4-channel adapter. This allows connecting 4 fibers at once, as you see it here, and that means typically you can connect your device under test to this connector adapter at a separate bench. So you just connect your device at a separate bench, and whenever the test system is available, you carry over this DOT with these adapters, and you can snap on these adapters in a very short time, much faster as if you were connecting the individual connectors. I would like to demonstrate to you now measurement results, and I have results here which have been obtained on a number of different components, and one component is a 40-channel AWG, and another component is a 16-channel multiplexer, demultiplexer based on thin film filter technology. I have an drop filter, also thin film, and I will demonstrate or show results obtained on a DPSK demodulator. This is a insertion loss result which has been obtained on a 40-channel AWG, and we see that these AWG channels, they have a noise floor somewhere or side mode suppression somewhere around 45 to 50 dB, and all these measurement, all the results which are displayed here on this screen, they have been obtained in a single sweep, as we discussed before. In order to have a useful evaluation analysis of these of all these measurement data, we are providing a dense WDM analysis function, and this allows you the software provides a number of parameters, like you get the peak wavelength and also the corresponding ITU wavelength, the ITU wavelength error. And so as you see, there are a number of results provided which are analyzed by the software. So that is something you can also just export to other applications and make use of that on your own. Here in this graph, you see now 40 channels. There might be cases where you would like to look at one individual channel, and so now here in this case we look at one channel. And as you see here on the left-hand side, you can select the channels which you would like to see. It's very simple, very easy. You just select the channels, and whichever is of interest to you, you can get it on the screen. You can also look at multiple parameters at the same time, as you can see here. So we have here the loss characteristics, and in addition the PDL characteristics of one of the channels. And looking at the PDL characteristic here a bit more in detail, so after zooming in, we see here that this particular device has a PDL of a level of about 0.02 dB. And so this measurement system allows you to highly accurately verify the components also for this PDL parameter. And I would like to move on and look here at a measurement example which has been obtained on a 16-channel multiplexer, demultiplexer based on thin film. And in this case, you see that this has a slightly higher side mode suppression compared to the AWG. So we have here a level of about 60 dB noise floor. And also in this case, as discussed before, this measurement has been obtained in a single sweep, so that did not require multiple sweeps at different gain settings. I would like to now look at an drop filter, and as you see here, that is just a channel filter, and on the top measurement here we see the loss. And one important function which I would like to introduce now is that is the TETM measurement function. So the loss characteristic, that is typically the curve, the measurement result, which is obtained with unpolarized light. But if you apply polarized light to the filter, then the filter may show principal states. And the two principal states are, in this case here, called TE and TM. And you see that there's a significant wavelength shift when moving from one principal state to the other principal state. This wavelength shift is really at the end, the result of PDL. So if you look here at the slope, you see that the difference between one and the other polarization is significant, and that translates into a high PDL level, as you see here. Then again, of course, at the crossing point, you have minimum PDL, which you see here on the PDL curve. We will look at this TETM function a bit later again, because it provides some further important information. This device which we look at here, that is a 50 gigahertz DPSK demodulator. So we see here on the top measurement curve the loss characteristics as you may expect. So that's the characteristic of a Mach-Sehender interferometer. And again, let's look first here at the third measurement from the top. These are again the TE-TM measurement curves, and you see also here in this case that there's a significant shift between the two principal states. And I have to admit that I did select here a measurement, a device which did show this significant shift, just to make it a bit easier to look at this effect and to understand the measurement capability here. So we see that we have here a shift between the principal states, and therefore, again, the same behavior here. We have a crossing point between the two curves, and at that point we have minimum PDL. Same at every channel here, moving on. Now, when designing DPSK demodulators, or when verifying the specification of such devices, this TE-TM shift is a very important parameter. So you would like to verify the polarization dependent frequency shift, and this is done by this software automatically. So for every channel, you see that we have here the wavelength shift obtained and displayed. And if you look precisely here, the wavelength shift here is in the order of 4.4 gigahertz, so which is, as mentioned before, quite a large wavelength shift. And again, in this case, you can export all these data. So you have here the data shown in this analysis table on the bottom. And by a very simple click on the icon here, you see the Excel icon here on the top of the screen. By a click on this Excel icon, you get all the data transferred to Excel, and you immediately have it there for further evaluation. You can also transfer this data to MATLAB or to other programs, or you can just save it as comma-separated values, for example. In total, now I would like to summarize the performance characteristics. This system has been designed to work in both windows, the 1.3 window and also the 1.5 window, so the SC and L band. And depending on settings, we can achieve wavelength resolutions far better than 1 picometer. And as we have seen, the dynamic range in a single sweep is 60 dB, but it can be much larger if we also go for multiple sweeps. The PDL repeatability is typically about 0.02 dB, and we can scale the number of channels in multiples of 4 up to hundreds or even further numbers. And the measurement time, as we mentioned before, it really depends on the settings, and the typical measurement time is between 10 and 20 seconds for 40 channels across the C-band. All this measurement capability is supported by Agilent's new N7700A photonic application suite. This is a new modular software platform which allows fast and easy characterization and analysis of optical components and signals. So currently, there are measurement engines available for multi-channel insertion loss, multi-channel IL, PDL, and insertion loss, PDL, PMD, and some further things. And so this software is available for download right now. So you can go to this indicated web page here and download the software and get it running on your computer immediately. So the full functionality of this software package is given during the first 60 days, which are considered a trial evaluation period. What is really interesting about this software is that it supports, of course, current, but also most of Agilent's legacy optical test equipment. So if you have some not so new anymore power meters or so in your lab, you can just download the software and use that for doing these measurements. So this legacy equipment typically can be used for doing multi-channel insertion loss measurements. The multi-channel insertion loss and PDL measurement that requires some of the newer capabilities which are included in the multi-port power meter, which we discussed, and so in that case you should have that new multi-port power meter. But what I would like to point out is all these functions are available for testing immediately after download, and after 60 days you may want to decide if you want to obtain a license, if you want to do IL and PDL measurement. But if you just want to continue doing multi-channel insertion loss measurements, that continues to be free. So you can just use that software. And I would like to show some further capabilities of the software. So there are a number of application packages available, and we discussed just before the insertion loss measurement. That is a free capability. We just provide it and you can use it. The insertion loss PDL component measurement that contains a number of functions, and that includes also additional functions like report generation and data export to Excel, to MATLAB, and we have automation interfaces here, as also mentioned before already. We can do the filter multiplexer analysis so that we can identify the ITU channels, for example, as seen before. We have an application package which covers polarization analysis and control. And also, some of you may know the Photonic Foundation library already. That library is also now part of this Photonic Application Suite software package. So as you may find, this is a very powerful package, and as mentioned, feel free to download that from this web page. I would like to briefly talk about automation, and that means really integrating the system potentially in manufacturing environments. So there are various interfaces so that the components of the software can be used on various platforms. And some examples are shown here. So you have a MATLAB interface. You can just export the data to MATLAB. The same with LabVIEW. You can obtain the data easily in LabVIEW and do your further processing, or your link to your database in your manufacturing environment, for example, using LabVIEW. And the same applies to H1V and Visual C++. If you would like to have some more information on these solutions, please feel free to also go to the web page for the Photonic Application Suite. That is, again, this web page as we discussed before. And if you are interested in some more information about polarization and dispersion solutions, the web page is given here. In conclusion, I would like to summarize. We have seen in this presentation that the new advanced optical networks really establish new requirements for test equipment. And throughput, floor space, and connectivity are critical, but I should say they continue to be critical, so that has been a movement for some time. But what is in particular now of interest is that the high capacity photonic switching networks, they drive the requirements for insertion loss and PDL measurements. And Agilent's new Photonic Application Suite has really been set up to support manufacturers of components and modules in really efficiently test their components considering these new requirements. In addition, we are supporting the legacy test equipment because this makes the transition simpler in your lab. So basically, in every lab in the world, we see adjuvant photonic test equipment, and therefore it should be easy to set up some simple measurement using that software and some existing test equipment. Also regarding PDL, we have seen that the adjuvant single sweep measurement method shows really high speed and high accuracy, as well as high robustness, so that you have a high reliability of the measurement results. This has the benefit that the multi-channel PDL test times have been reduced from what has been several minutes in the past down to a few seconds today. I would like to thank you very much for your attention during this presentation, and I would be happy to receive questions from you if there are any further open points on your side.
Ladies and gentlemen, if you do have a question, please press the 1 key on your touch-tone telephone. If your question has been answered or you wish to remove yourself from the queue, you may press the pound key.
I believe there are a couple of questions in chat. Harold, if you want to ask
actually, Emily, this is true. I sorted some questions out. I think this one is a good one. Ralph, can you comment on PDL measurement with angled connectors?
Yeah, that's a good one. You know, usually of high interest to have really accurate PDL measurements, and on the other hand, it's also desired to have a reliability when connecting components, and so you want to be independent of possible dirt on the connectors, and so many people like to use angled components, angled connectors. So, but there is a very strong compromise if you use an angled connector, because such connectors, they themselves exhibit a PDL level of about 0.02 dB. So if you have a component with two such connectors in the path, one on the input and one on the output side, you have two sources of 0.02 dB of PDL. And as we discussed before, depending on the polarization state of the component in between, this PDL may add up or that may cancel out. So you have an uncertainty which is going up to 0.04 dB. As a result, I would recommend, if you are really concerned about PDL, you should really use either straight connectors or possibly splice your components into the path. If you use angled connectors, then you have to accept this compromise. Okay, thank you for the question.
Okay, do we have meanwhile questions from the audio line?
I am not showing any questions at this time.
Okay, then I'll go ahead with the next one. The next one is about the wavelength resolution. What kind of wavelength resolution is possible with a single sweep PDL?
It depends on the settings of the system. So if there is interest on high wavelength resolution, we can obtain resolution values which are around 0.1 picometer. So this is a really high resolution, gives you lots of data points, and if that is of interest, then we can go down to that level. But in case you do not need such a high resolution, of course, there is the possibility to have a lower resolution in order to not to make the data files too large. Thank you very much for that question.
Okay, here's one. Okay, I just read it. It's is there a length limitation for the device under test?
No, there is not length limitation. So you can basically use a device with any length. However, what you have to be aware of is if you have a very long device, like a very long fiber, possibly a fiber link, you may run into a limitation of the dynamic range. So as we mentioned, if you want to cover the measurement in a single sweep, you have a limitation of about 60 dB. In case of single mode fiber, this translates into a certain length, but apart from that, there is not really a length limitation.
I think this question was about the interferometric measurement methods, right? They usually have a length limitation.
Yes, there are other methods which do have a length limitation, and they are mostly usable only for short devices and not for long fibers.
Okay. Emily, do we still have time for another one?
Yes, I think we have time for one or two more. If we don't happen to get to your question, remember that Ralph will follow up via email.
Okay. Okay. Yeah, here's one. Can the PDL measurement be done on an amplified link?
Yes. In fact, we have done that. We have done PDL measurements on amplified links. However, of course, you need to consider in that case that there is a strong dependence on the system behavior. So you may run into problems if the, for example, if the control loops of the amplifiers are really fast, and if you're changing your polarization and the control loops of the amplifier always control out the power variation which is caused due to PDL, then of course you do not get a useful measurement. Therefore, you may have to also play with the system you're measuring on. But we have done measurements in the past, and they have turned out to work very fine.
Yes, maybe one comment of myself. Actually, you have to really play with the EDFAs normally to turn off the automatic switch off when there's no power and these kinds of stuff. But yes, we get actually quite good measurements with that.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.